Good day, I'm Norman Wildberger. In today's lecture, we're going to look at a somewhat more advanced topic where we take our projective quadruple quad formula and apply it to the interesting classical question about the relationship between the sides of a cyclic quadrilateral and the radius of the circle that contains that quadrilateral. So today's lecture is going to be sort of the culmination of a series of videos that I've been making that show you how to start thinking about geometry algebraically. And we basically just started with a one-dimensional point of view, both in the affine and the projective situation. And we've seen that this one-dimensional point of view really has extensions in a lot of different directions and allows us to reformulate many classical important results. And that will also be the case today. So there'll be some algebraic, say, sophistication a little bit today. But still, I hope you can follow it all. Okay, so we're going to go back in time to another very fabulous and interesting result called Parameshvara's formula. Okay, so it's a formula for the radius, little r, of a circle that contains a cyclic quadrilateral with side lengths, little a, b, c, and d. So Parameshvara was an Indian mathematician who lived in Kerala. It's a state in the southern part of India that had a very vibrant mathematical and astronomical history and heritage, and at this time they were very prolific work being done there. Okay, and here's his lovely formula, which is a little bit reminiscent of Brahmagupta's formula. In fact, it contains a term very much like the one we find in Brahmagupta's formula. So it's that r squared equals the product AB plus CD, AC plus BD, AD plus BC, divided by 16 times S minus A, S minus B, S minus C, S minus D, where S is this semi-perimeter term that we've seen a number of times now, the sum of the four side lengths divided by 2. Well, we can rewrite this because we recognize that this denominator here is exactly what we call the quadria of this cyclic quadrilateral. I remind you that was ultimately 16 times the square of the area. That script A stands for quadria. So this is just a little bit shorter way of writing it. And if we want to write things purely in terms of the four lengths, A, B, C, D, we can replace this expression with this expression here. So a very beautiful formula. And although it's very nice, for us, again, it's problematic because it's all in terms of these lengths. And we know that lengths in two-dimensional geometry are, in fact, transcendental quantities. They're things that you can only obtain by running infinite processes, typically a square root process, to infinity. Okay? So although they are, so maybe physically, very seemingly natural notions, mathematically they are more problematic. And we would like to frame this result in an alternate way, purely algebraically, involving the quadrances of the various quantities instead of the actual lengths. So you will know by now that my point of view towards mathematical theories is that they should be supported by examples. We should be able to explicitly lay out a situation which encodes our abstract theory, where everything is precise and concrete, and we can check the various claims made by actually making complete and correct calculations. So let's have a look at Parameshvara's formula in a specific example. I'm going to choose, for something a little bit different, the circle x squared plus y squared equals 2, okay, which has a circumquadrance of 2. Goes through the point 1, 1. It goes through some other points as well. For example, you can check that these various points that I've got here are also points on this circle. Here we have minus 7/13 and 17/13. Here we have 23 over 17 and minus 7 over 17. And here we have minus 7/5, minus 1/5. And I hope you know or can figure out how we could generate more such points on such a circle. So let's take that particular cyclic quadrilateral and work out all the various things. Okay, so A, which is the length of that side. All right, so we have to take the difference here and square it, take the difference here and square it, add those two squares, and then we have to take the square root, as we like to do, don't we? We take the square root. We spend the rest of eternity generating more and more digits of this square root, and at the end of eternity, there it is, the square root. Right, so what we end up getting is that A is 4/13 the square root of 26. This happy little notation allows us to shortcut the actual infinite process and pretend that we have done that process, while in fact all what we've really done is just write a little bit of a squiggle with a 26 under it. Similarly, we can calculate that this length B is 6/17 times the square root of 17. This length C is 18 over 85 times the square root of 170, and D is 14/65 times the square root of 65. And from my point of view, all of these statements are very much in quotes, right? Because I actually do not believe in the existence of any of these objects. And neither should you. So what we're doing now is playing along with the standard game. Okay, so if we wanted to play the standard game and verify Paramesh-Varas formula, well, here it is again. Now, r squared, the numerator there, the denominator, all in terms of A, B, and C, and D. Now, what is r in this case? Well, r is the square root of 2, the radius. R squared, conveniently, is 2. Okay, that's good, that's at least rational. So the claim is that if we replace little a, b, c, and d in this big formula with all of these things and make the calculation, then at the end we get 2. So does it work? Well, I encourage you to see whether it works. Right? So what we have to do is we actually have to make a real number calculation. We have to stick these things in here, and we have to take a times b, to multiply this times this. We have to multiply c times d, and then we have to add those two things. Okay? Then we have to do the same thing for this expression, the same thing for this expression, and then we have to multiply this real number times this real number times this real number. Well, on my computer, if I set the accuracy to 10 significant digits, and I ask my computer what the numerator is here after having done that computation, I get 327.3094261. Of course, we all know that's not really the correct answer, is it? There's a few trillion, in fact, there's an infinite number of digits that we have truncated conveniently. But they're there, aren't they? Oh yes, they're there. What about the denominator? Well, the same kind of story. You plug all these things in, make the calculation, and the computer tells you that you get 163.654713 ... Right, and then I get my computer to calculate this thing divided by this thing, equals, and my computer tells me that I get 2.000000001. Okay, so have we verified Paramesh-Varas formula? What do you think? Well, it's certainly the case that they're pretty close. The left-hand side and the right-hand side are pretty close. Are they exactly correct? Well, that depends, really. I mean, if we're talking about exact correctness, then every single one of those infinite amount of decimal digits that we are dropping is actually important. You change any one of them just slightly, and then you're going to get inaccuracy. You're going to get an incorrect result. So how are you going to actually verify that the formula is actually correct in this case? Precisely correct. So I urge you to to have a go at this, try with your calculator, see what happens when you make this calculation. All right, so there's also a non-convex form of Parameshvara's formula. And this is the situation that we're imagining. We have a cyclic quadrilateral, but now not a convex one, but rather one that goes A, B, C, D like this. Okay, it's still consisting of 4 lengths. Still we have 4 points on a circle. We can still ask for the relationship between the 4 lengths and the radius r. And here is the non-convex form of this result. R squared is now AB minus CD minus AC plus BD and AD minus BC. And the denominator is also a little bit different. It's 16S times S minus A minus B, S minus A minus C, S minus A minus D, where S is, as before, the sum of the 4 lengths divided by 2. Well, we can recognize that this can be written this way here. This denominator is, again, the quadria of this non-convex quadrilateral. 16 times the square of the area still makes sense for a non-convex quadrilateral. And in fact, we've seen that in this case, the quadria can also be written this way here. So it's a little bit like the Brahmagupta formula, but the nature of these things is different. There's either 0 minus signs or there's 2 minus signs in various places. Now, I'm not sure where this result was actually first established. I'm pretty sure that Parameshvara didn't have this formula, but I suspect it was probably a 19th century development, but I'm not really sure who to credit this formula for. So if any of you know, I'd be kind of curious as to what the origins of this variant are. So let's have a look at an example in this non-convex case. We'll choose the same circle as we did previously and the same 4 points on it, but we'll traverse those 4 points in a non-convex fashion, say from here to here to here to here to here. So with lengths A, B, C, and D. Okay, we can compute those lengths. A couple of them are familiar, and there'll be 2 new ones. There's A, there's B, there's C, and there's D. Okay, and here's our formula for r squared, which should be 2 in terms of these 4 numbers. And again, we can try to do this real number arithmetic, but of course we're not really able to do this real number arithmetic. One is never able to do the real number arithmetic unless it's a triviality. It's just the way it is. But we can pretend that we're doing the real number arithmetic, as we do, and plug these things in, do everything approximately. So on my computer, the numerator is 24.455676618. The denominator 12.227838009, and of course I've left off all those other trillions of digits. And then when I ask my computer to evaluate this quotient, it tells me that the answer is 1.999999999, from which I conclude that this is a pretty good formula, but is it actually correct or not? Not so clear, is it? Even verifying it in this one particular case to say whether it's actually completely true in this particular case is rather challenging. That's the way it always is when you're doing real number arithmetic. It's always a challenge, which is why texts carefully avoid actually laying out examples like this, because it would become very quickly obvious to students that, wait a minute, there's a little bit of pulling the rug here. Okay? There's some obvious inadequacy in making claims about things which are based on this real number arithmetic, which we can't actually do completely. So we would like to establish an algebraic reformulation of Parameshvara's formula. One that we could, first of all, generalize to arbitrary fields and to other geometries like the red geometry, and one that we could actually verify completely by doing finite ordinary high school arithmetic on specific examples. Okay, so it turns out that the key formula that we're going to need is one that we're pretty familiar with, but a rather imposing one. It's the projective quadruple quad formula. Okay, so I remind you that here is our core circle with the equation x squared plus y squared equals x. Here we have a cyclic quadrilateral on that core circle. And here are the quadrances now, capital A, capital B, capital C, capital D. These are the purely algebraic equivalents of the lengths. They are just given by the sums of the differences squared of the x and y coordinates. And we know that in this particular case, for this particular circle, these four quadrances satisfy R of A, B, C, D equals 0, where R is our projective quadruple quad function. And we determined that because this formula originally came from the one-dimensional situation involving these projective 1 points. So it turned out that the projective quadrants between this projective 1 point and this projective 1 point is the same as this affine quadrant's capital A. So it was the relationship between the four projective quadrances of those four projective 1 points that allowed us to conclude that there's this corresponding relation between these four quadrances of this core circle. Now this core circle has a circumquadrance of 1/2 squared, or 1/4. The diameter quadrance is 1. And we saw this situation when we were talking about the triple quad formula and the triple spread formula, that the dilation of this basic circle affected the formula, in the sense that this is not a homogeneous formula, and so we ended up seeing that the amount that we dilated by got involved in the formula. So exactly the same kind of situation is going to be playing a big role here. Okay, but this is the sort of the important thing that we need to understand. I'll have to remind you about this projective quadruple quad formula. All right, so here's our projective quadruple quad formula, and it was quite a imposing a function. So R of, say, A, B, C, D is, so there's some big quantity all squared, and that big quantity has A plus B plus C plus D squared in it, minus 2A squared plus B squared plus C squared plus D squared, and then minus 4 ABC plus ABD plus ACD plus BCD, and plus 8 ABCD. So all of that squared, and now we subtract from that 64, the product ABCD, times the product 1 minus A, 1 minus B, 1 minus C, 1 minus D. Okay, there was some kind of higher dimensional extension of the affine quadruple quad formula, which it reverts to if A, B, C, and D are small. We could ignore terms with higher degree. Now, when we get to more complicated formulas like this, it's very useful for us to employ some notation that comes from the theory of polynomials, and symmetric polynomials. This is something that we are going to be talking about. It's a very interesting topic, but let me just informally introduce four important things called the elementary symmetric expressions in little a, b, c, and d. So these are expressions that we can write down that are sort of symmetric with respect to these things. If we interchange two of them, it doesn't change. So there's E1, which is just the sum of all four. There's E2, which is the sum of all possible products of different ones. So AB plus AC plus AD plus BC plus BD plus CD. So all the possible ways of multiplying two of these things. E3 is ABC plus ABD plus ACD plus BCD. All the possible ways of multiplying three of them together and adding them up. And E4 is just the single product of all four of them. Okay, so here's an interesting exercise for you to show that you can rewrite this thing here more compactly by sort of using these as the building blocks. So we can write it as E1 squared minus 4E2 plus E3 all squared minus 16 E1 minus 2 squared times E4. It's a pleasant kind of thing. In particular, if, say you decided to set d equal to 0, well then this term here would become 0, so that whole term would disappear, and then you would just end up with this thing here. You might like to see what that thing is. Alright, so there's a pleasant rewriting of this thing, showing that this thing is in fact a symmetric polynomial. And there's in fact a very important theorem around that goes back to Newton, which is that basically any symmetric polynomial that you can write down in a, b, c, d can be written this way as some combination of these elementary symmetric polynomials. So there's some interesting theory around here, which I am going to be talking about a little bit later on. We need a little bit more talking about polynumbers in different dimensions to do that correctly. Alright, so here is my version of the Parameshvara formula in a purely rational algebraic formulation. We'll call it the cyclic quadrilateral circumquadrance theorem. And it is that if a cyclic quadrilateral has quadrants A, B, C, D on a circle of quadrants K, so a situation like this is a circle of quadrants K. We have a cyclic quadrilateral. Quadrants are capital A, capital B, capital C, capital D. Then the relationship between these five things is given by this algebraic equation. P times k squared minus 2qk plus r equals 0, where p, q, and r are expressions obtained from the four quadrants. P is q of a, b, c, d, where that is the quadruple quad function, the affine one, which is given by this expression. I hope you remember that, or at least that it looks familiar. The q here is this expression. It's a little bit more complicated. So there's an AD minus BC times BD minus AC times A plus B minus C minus D, plus a similar kind of term AD minus BC times CD minus AB times A minus B plus C minus D, plus a similar kind of term BD minus AC times CD minus AB times minus A plus B plus C minus D. And finally, where this R equals the product AD minus BC times BD minus AC times AB minus CD. Okay, and this formula appeared as Theorem 111 in my book, Divine Proportions. There's lots of interesting theorems in my book, Divine Proportions, and if you really want to go in this direction and understand sort of algebraic mathematics more deeply, after you've gone through these lectures, probably be a really good idea to go through my book very carefully. There's a lot more material there, a lot of additional insights and opportunities for learning mathematics correctly. Okay, so we want to see, well, how does this thing work? And why is it true? And how does it connect with the Parameshvara formula that we've already seen? It looks, on the surface, to be quite different. So let me give you an example. In fact, let's have a look at the same example that we looked at earlier over the real numbers, and now we're going to look at it over the rational numbers, the way God really meant us to look at things. So here are our same points, but now the relevant objects are the quadrances. So just difference in x coordinates squared plus difference in y coordinates squared. So calculating a quadrant is something you can do with pen and paper. It only takes you a minute or two, and at the end of that minute or two you have the exact answer, no waffling necessary, no appeal to infinite processes, no pots of gold at the end of rainbows. So capital A is 32 over 13. B is 36 over 17. C is 648 over 85. D is 196 over 65. And our quadrants K is going to be 2, the quadrants of this circle. Okay, so here is our theorem. that the relationship between these five things is that pk squared minus 2qk plus r equals 0, where p, q, and r are those rather lengthy expressions built from these four numbers. Okay, there may be lengthy expressions, but it's all just high school arithmetic. You're just multiplying, adding, subtracting, maybe a bit of division, but no, there's no division. Just adding, multiplying, and subtracting. And you can calculate these quantities, and then you can write out this quadratic equation. And it turns out that that quadratic equation factors. And here's what you end up getting. So you end up getting some constant, which is this big fraction, because there's lots of numbers that appear. But when the smoke clears, the quadratic that you've got factors as k minus 2 times 24,359k minus 12,430. From which you can conclude that k equals 2, or k equals 12,430 divided by 24,359. So the algebra is giving us a solution to what we want. It's also giving us some additional information. This is another possibility that perhaps corresponds to a situation where the data is the same as what we've given it, but maybe the picture looks different. Or maybe it's something that's visible in some other kind of geometry. In any case, the algebra is suggesting that this is not the entire story. There's something else out there as well that we could look at if we were interested. But if we were only interested in figuring out what this quadrant was in this particular situation, we could deduce that k equals 2 after examining the various possibilities numerically using our picture. So I hope we appreciate the difference, the huge difference between this kind of arithmetic and the previous kind of arithmetic involving real numbers. We can actually lay out the example, make the calculation, everybody can check. There's no cheating, it's completely solid. This is mathematics. Okay, so a fundamental question is, how do we establish this cyclic quadrilateral circumquadraence formula? pk squared minus 2qk plus r equals 0. A formula for the circumquadraence of the circle which contains a cyclic quadrilateral with these quadrants as A, B, C, and D. And P, Q, and R are those rather lengthy expressions built from the A, B, C, and D's that I showed you on the previous page. So it turns out that it's actually rather conceptually simple and follows very much along the lines of an earlier investigation on the relationship between a triangle and the quadrants of the circle that goes through those 3 points. So the basic idea is that if we have a cyclic quadrilateral like this with quadrants as A, B, C, D, and circumquadrants K, then if we rescale things so that we end up with a circle which is the same size as a core circle, then we know what the relationship between the corresponding quadrants is. It's given by our R formula. And what do we have to rescale by? Well, if the quadrants here is K, then the diameter quadrants is 4K. So what we need to do is we need to rescale by 4K. So in other words, if we divide each of these quadrants by 4K, then we're going to get 4 quadrants which lie on a core circle. And then the R function applied to them will be 0. So R of A over 4K, B over 4K, C over 4K, D over 4K equals 0. This follows from rescaling and the fact that we know about the story for a cyclic quadrilateral on the core circle. And it turns out that when you take this expression and you sort of clear the denominators, you will get, somewhat surprisingly, a quadratic equation in K, and it has exactly the coefficients that I said it did. So this is a great exercise for you to do to show how this formula follows from this one, basically just by clearing the fractions. So it's really a very remarkable thing that it really comes down to this one-dimensional result, about 4 projective 1 points in this one-dimensional projective line situation. Alright, so let's have a look now and see why this formulation incorporates the Parameshvara kind of formulas, both in the convex and the non-convex situation. So, with this quadratic equation, if we were interested in the two solutions, say K1 and K2, then the product of these two solutions is going to be R over P. It's a general fact of a quadratic equation. And R was this product here, and P was the quadruple quad formula applied to capital A, B, C, and D. Now suppose that our quadrances are actually squares of things. So suppose that we have some lengths around, say little a, b, c, and d. So that little a squared is capital A, little b squared is capital B, and so on. Then each of these terms in the numerator is going to be a difference of squares. So that this thing here will actually be little ad plus bc times little ad minus bc. And similarly, this one here will be bd plus ac times bd minus ac, and this one ab plus cd, ab minus cd. So these are the numerators that appear in the convex and non-convex form of the Parameshvara formula. And what about the denominator? Well, we have to remember that when we have cyclic quadrilaterals, and we know the quadrances, then the quadrias are also determined by a quadratic equation. That's what we call the cyclic quadrilateral quadria theorem. And part of that told us that the product of those quadrias is going to be exactly this quadruple quad function applied to A, B, C, and D. So we can take this term and separate it into the quadria of the convex quadrilateral times the quadria of the non-convex quadrilateral. And when we do that, we see that this is exactly the formula for the R squared, or the K1 value for the Parameshvara formula in the convex case, and here it is for the non-convex case. So our formula somehow is getting both the convex and non-convex situations at the same time. It does not want to separate them because the algebra does not want to distinguish between the convex and non-convex case. The algebra doesn't see that so clearly. It just wants to treat them together. And treating them together, since there's two of them, is natural to give a quadratic equation. So this is something that we have to expect with this approach to mathematics, that the algebraic approach is going to get bigger in complexity and degree as the number of options increases. So the algebra wants to take care of all the possibilities at once, so to speak. That's a very nice orientation to have, an important understanding to have, that we want to look at all the possibilities at once, and the algebra helps us to do that. So I think that I have given you, over the last dozen or so videos, plenty of solid evidence to support the idea that thinking algebraically about fundamental geometrical concepts is a powerful idea. So we've been able to look at Heron's formula, Ptolemy's theorem, Brahmagupta's formula, Bretschneider-von-Stout formula, the Parameshvara's formula, and we've been able in each case to, first of all, state them completely clearly and accurately, give proper proofs, completely algebraic, watertight proofs, and generalize them both to more general fields and to other geometries. It's a major accomplishment, really, if you think that these are historically amongst the most important formulas in all of mathematics. And there's clearly a lot of new opportunities to keep going in this direction. We can see that we've just really been scratching the surface because we've only really been investigating one-dimensional geometry and the various consequences of some simple formulas from there. There's still two-dimensional geometry waiting to be laid out, and I will eventually do that. And then three-dimensional geometry, higher dimensional geometries, a lot of more extensions. A lot of you might want to play around with those directions yourselves. So it's time now for us to turn our attention to modern set theory. There are a lot of very serious weaknesses with that subject, unfortunately. And many of them are intimately connected with the weaknesses in modern analysis, starting from the construction of real numbers and their arithmetic. We'll have a look at set theory from a larger point of view, thinking of that as only one aspect of a larger sort of understanding of data structures in mathematics. But probably a good place to at least start a conversation about this is with a very simple and fundamental question of what exactly is a set. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.